In this video, I'll show you how to solve the ALEKS problem called limiting reactants. This problem is not going to be hard, but it is going to be tedious. The first thing that we need to do is use the words in this problem to write a balanced chemical equation. This problem is telling us that we have aqueous sulfuric acid, H2SO4. Don't worry about writing the states like aqueous or solid or liquid. That doesn't make a difference in this problem. The aqueous sulfuric acid is reacting with sodium hydroxide, so NaOH, and it is producing, so the products are sodium sulfate, Na2SO4, and liquid water, H2O. So once we get these reactants and products written down, we need to take a look at this equation and make sure that it is balanced. And a lot of times they are just going to be balanced the way they're written. On the left-hand side, we have 1, 2, 3 hydrogen, and on the right-hand side, we only have 2. That means it's not balanced. So let's go through the process of balancing this equation. On the left side, we have hydrogen, sulfur, oxygen, and sodium. On the right side, we want to make that same list in the same order: hydrogen, sulfur, oxygen, and sodium. On the left-hand side, initially, we've already counted our hydrogen. We have 3. We have 1 sulfur. We have 1, 2, 3, 4, 5 oxygen atoms, and we have 1 sodium. On the right-hand side, we have 2 hydrogens, 1 sulfur. We have 1, 2, 3, 4, 5 oxygens, and 2 sodiums. So I can see that right away we already know the hydrogens are not balanced. We need to have more hydrogen over on the right-hand side. And hydrogen is in this molecule right here. Currently, the coefficient in front of the H2O is a 1. I'm going to increase it from 1 to 2. That's going to give me a total of 4 hydrogen atoms on the right-hand side. 2 times 2 is 4. And because there's also oxygen there, that's going to change the number of oxygen atoms on the right-hand side. So now we have 1, 2, 3, 4 oxygen plus 2 more, which is a total of 6. And if we keep looking, our hydrogen's still not balanced. We have 3 on the left, 4 on the right. We need more hydrogen on the left-hand side. Hydrogen is present in 2 molecules on the left-hand side. And in a situation like that, like I don't know which one of these I should be increasing. When I'm in this scenario where I need to increase the hydrogen and there's 2 ways to go about doing it, I'll just skip it. I'm going to skip it for now and move on to the next atom. The next atom is sulfur, and sulfur is already balanced. Looks good. The next atom is oxygen. Oxygen, I have 5 on the left, 6 on the right. I need more oxygen on the left. Again, we're in this same boat. We have oxygen in 2 spots. I don't know which one of these molecules I should be increasing, so I'm going to skip it. And I'm going to move on to the next atom. 1 sodium on the left, 2 sodiums on the right. I need more sodiums on the left. Sodium is located only in this one place. Currently, the coefficient is 1. I'm going to change the coefficient to 2. That's going to change the amount of sodium from 1 to 2. It's also going to change the amount of oxygen and hydrogen because this molecule also has oxygen and hydrogen. So now on the left-hand side, I have 1, 2, 3, 4, 5, 6 oxygens. And I also have 1, 2, 3, 4 hydrogen. And look at how this problem solved itself. My hydrogens have balanced themselves and my oxygens have always balanced themselves. That's always going to be how this works. It's super nice. So what I'm going to do now is erase the notes that I have here that I used to help me balance the equation. The equation is balanced. We're ready to move on to the problem. The problem tells us that we have 8.8 grams of sulfuric acid. That's this molecule right here. I'm just going to make a note of that. And we also have 2.16 grams of sodium hydroxide. And it's asking us to calculate how much the mass of sodium sulfate we can make. So this is a limiting reactant problem, meaning that either the sulfuric acid is going to be controlling our mass of sodium sulfate or the sodium hydroxide is going to control the mass of sodium sulfate. We don't know which one it is, and the only way to figure it out is to do 2 calculations. So we have to do 1 calculation for the sulfuric acid to figure out how much sodium sulfate can be made, and then we need to do a second calculation for sodium hydroxide to figure out how much it can make, and then we'll compare those 2 numbers. So for the first calculation, we're going to start with our mass of sulfuric acid, 8.8 grams, and we are going to convert that 8.8 grams of sulfuric acid into moles of sulfuric acid. We want the gram H2SO4 unit down on the bottom so that it cancels itself out, and we want to convert into moles of H2SO4. The conversion from gram to moles is done using the atomic masses of all of the atoms in this formula. So we have 2 hydrogen atoms, we have a sulfur atom, which is 32, and then we have 4 oxygen atoms, which are each 16. Now, when you are doing a problem like this on ALEKS, it's going to be super important that you do not round these atomic masses like I just did. I'm getting 98 grams per mole, but I guarantee you that if I used 98 grams per mole to solve this problem and entered that number into ALEKS, it would be marked wrong because ALEKS does not like these numbers to be rounded. So when you're working on this problem yourself, don't use 32 as the mass of sulfur. Look it up. It's 32 point something. I don't know what it is, but use those more exact masses so that you can get this problem correct. Next thing that we need to do is convert from moles of sulfuric acid into moles of our desired molecule, Na2SO4. Na2SO4, and we do this conversion using the stoichiometric coefficients from the balanced equation. That's why we had to balance it. The moles of sulfuric acid, its coefficient is 1, so this is going to be a 1, and the sodium sulfate, its coefficient is also 1, so it's also going to be a 1. It doesn't always work out that way, but that's how it's worked out in this situation. Now, our last step here is to convert out of moles of Na2SO4 into units of grams Na2SO4. And I'll show you another shortcut if you don't feel like adding up these molecular weights all of the time. I will show you that you can just Google them. Molar mass of Na2SO. It's even like starting to autofill it for me. That is, and you should always double check, always, when you're using the internet for things like this, you should always double check that it did not autocorrect or like search the wrong molecule. The molar mass of sodium sulfate, Na2SO4, is 142.04 grams. So this is going to have like all those sig figs that ALEKS wants it to have. And that's a really huge time saver, especially when you're working on a tedious problem like this. So that is the mass of 1 mole, and we can cancel those units out like that. And this will allow us to calculate the mass of Na2SO4 that we can make from 8.8 grams of sulfuric acid. 8.8 divided by 98 times 142.04. So what we have done is decided that we can make 12.75 grams of Na2SO4 if we are starting with 8.8 grams of sulfuric acid. Now, like I said, this is not a hard problem, it's a tedious problem. We have to do this calculation a second time. We have to repeat the calculation this time, starting with our 2.16 grams of sodium hydroxide and converting into a mass of Na2SO4. So tedious. We're going to basically do the exact same thing. We're just starting with a different molecule and a different mass. 2.16 grams of sodium hydroxide, NaOH. We need to begin by converting that into moles. So 1 mole of NaOH is, sodium is 23, oxygen is 16, hydrogen is 1, so that's 40 grams of NaOH per mole. And then we need to do our mole to mole conversion. We want moles of NaOH down on the bottom because we want to cancel that unit. We want moles of Na2SO4 on top. And these numbers are coming from the balanced equation. For the moles of Na2SO4, we need the stoichiometric coefficient, that's a 1. For the moles of NaOH, we need the stoichiometric coefficient, it's a 2. In the balanced equation, we have 2 moles of NaOH. And let's take a look at how our units are canceling. The last step here, we want to cancel units of moles Na2SO4, so we want that on the bottom. We want to convert into the grams of Na2SO4, so we want that up on top, using the molar mass, the molecular weight of Na2SO4. So we'll do all of the math again. Like, as you can see, this is basically the exact same problem that we've done twice. once for each one of those reactants. And for this one, I get 3.835 grams of Na2SO4 that we would make from the 2.16 when we're starting with the 2.16 grams of NaOH. So after we've done the calculation twice, we've come up with two numbers. Only one of them can be right. We have to decide which one is the answer to this problem. And this is where students get really hung up. The wording of the problem is saying, where is it? Calculate the maximum mass of sodium sulfate. So logically, when people see maximum mass, their eyes are going to be gravitated to the larger number, 12.75. That's a bigger number. That must be the maximum mass. And that's actually not how this works. That's not what this is telling us. The maximum mass is the smaller of the two numbers. So that's like that in a nutshell. I'll just go ahead and write that in. It wants it to 3 sig figs, so that's going to be 3.84. And that might seem totally backwards to you, but what these calculations are telling us, what we've got from this, is that we have determined that we have enough enough sulfuric acid to make approximately 13 grams. We have enough sodium hydroxide to make approximately 4 grams. Or another way of saying this is that we only have enough sodium hydroxide to make this 3.8 grams. Even though we have enough sulfuric acid to make 12.75 grams, it doesn't even matter because we're going to run out of sodium hydroxide. The most that we're going to be able to make is limited by the small amount of sodium hydroxide that we have. So even though it's telling us maximum, the actual answer to this problem is always going to be the smaller result from these two calculations.